All right, so I'm looking at the columns of this matrix. So I've got this vector A1, this vector A2, this vector A3, and this vector A4. So I'm trying to see if this set of vectors are linearly independent or dependent. So I could set up the homogeneous equation of AX equals 0, or I could stop and think, wait a minute, I see that there are more vectors than entries. So I have 4 vectors in R3. So that means for sure I have a dependent relationship. All right, so let's get into some more challenging ones. So I want to find H that make them dependent. So I want to make them dependent. So I know I'm going to set up the homogeneous equation with the augmented matrix, and I'm going to have to do row operations. So 1, negative 2, 3, 0, 5, negative 9, H0, negative 3, 6, negative 9, 0. That's the first step. So I see I'm going to have to take a negative 5 times row 1 and add it to row 2, and a 3 times row 1 and add it to row 3. So if I do that, keeping row 1 the same, and I get a row of zeros down here. Okay, so let's look and see what this means. So this, remember, let's have context here. This is x1, x2, x3, because I'd have 3 variables in front of each of my 3 vectors. So I see that I have a free variable, so I want to make sure I keep it free, but there's nothing I need to do to make sure that this row here has no pivot. So as a result, H can be any real number. Because of this row of zeros, it's always going to be dependent. All right, maybe let's look at a little different one here. So here I have a set of vectors. I'm going to do the same thing, augmented with zeros. 4, 6, 8, and 0. Okay, so then I'm going to take the time to multiply row 1 by 2 and add it to row 2, and 4 times row 1 and add it to row 3. All right, so this row 1 stays the same. Row 2 turns to this, and row 3 turns to this. Okay. So if I want them to be dependent, I want a free variable. So in order to get a free variable, I need for this to be equal to 0. So dependent if H plus 38 is equal to 0, so that means H has to equal negative 38. All right, so here we're going to get into playing with sizes of matrix and thinking about them. So if I'm looking at a 6 by 4 matrix, how many pivot columns, mind you, do I need to have for there to be linearly independent? So let's get a sense of the size of this matrix. So 1, 2, 3, 4, 5, 6 rows and 4 columns, right? So I'm looking at this. Okay, so that's the size of the matrix that I'm looking at. So to make them independent, I want to have only the trivial solution. So this is just the matrix, right? This is just the matrix A. It's not the augmented matrix. So if I have a pivot here, and I have a pivot here, and I have a pivot here, and I have a pivot here. So if I have 4 pivots, then I would have only the trivial solution. You don't need a pivot in every row. I need to be able to say that there's an x1 times the first, plus an x2 times the second, an x3 times the third, and x4 times the fourth to equal the 0 vector. So if I have 4 pivots, then I can find that they are linearly independent. So what it's going to translate to is if I have a pivot every column, that means linear independence. Okay, so how many pivots to columns do I need to have for the columns to span? So you remember that big theorem too. In order to span R4, okay, so in order to span a system, you need to have the number of pivots. But let's think about this. Wait a minute. I've got, if I'm looking at these vectors here, these elements are in R6. So if I have a 6 by 4 matrix, there's no way I can take linear combination of things that are in R6 to get to spanning all of R4. So vectors in R6 cannot span R4. They're completely different animals.